Let's just go through in order. Let's go through graphing calculator test. Here we go. Here we go. All right, find an equation for the line tangent to the curve at the given point, which I conveniently have set up right there. How about that? Okay, so the line tangent to the curve. What do we got to do here? Derivative. Yeah, we need a slope and a point, right? Okay, the point we can get without calculus. When x is 1, whoops, when x is 1, y is just equal to 1 cubed plus 3 over 8 times 1, which is 4 over 8, which is 1/2. Very good. So we've got a point then at x equals 1, y equals 1/2, right? Now we need a slope. So to get the slope, we equate the slope with the first derivative, right? That's what that means. The first derivative is equal to, the value of the first derivative equals the slope of y, or of the original function. So y prime equals, now how are we going to do this? Before, I don't want to jump into y prime yet. Talk to me about taking this derivative, because calculus is complicated. I mean, maybe we want to jump in and do the quotient rule, or maybe we don't.
1/8 squared plus 3.
Okay, good. Why not? Whenever we can, we always want to pre-write the function in a way, simplify it in a way that's going to make the calculus easier, right? And so why not do this? If we've got y equals x cubed plus 3 over the common denominator, 8x, split the fractions. Write that as x cubed over 8x plus 3 over 8x. Right, now what's this become? X squared over 8. Yeah, because I have x cubed over x is x to the 3 minus 1. Right, and cancel an x top and bottom. So x squared over 8 plus, if I have an x on the bottom, I put an x to the minus 1 on the top, right? That's an x to the positive 1 on the bottom. So it's 3x to the minus 1 over 8. Right? That makes things easier. Now, if I differentiate, what do I get from the first one?
1/4.
Yeah, because I've got this 1/8 that I can just ignore, right? When I differentiate, the only part that I'm differentiating here is just the x squared part, right? So I'm going to bring the 2 down front. Derivative of x squared is just 2x to the 1, right? By the power rule. So the 2 over the 8 would reduce to a 1/4 x to the 1. Okay. We okay with that? Does that make sense?
Yeah.
Okay. Second one. I've got the 3/8 that I can just forget about. Just pull that out front, and I'll multiply that by my answer that I get from the derivative of x to the minus 1. What's the derivative of x to the minus 1?
Negative 3x to the minus 2.
Good. Okay, I'm going to get negative x to the minus 2, but then the negative times the 3/8 makes it a negative 3/8 x to the minus 2. Good. Okay, I could rewrite that if I want to, just to make it a little simpler. That's just going to be x over 4 minus 3 over 8x squared. We'll put the x on the bottom with a positive exponent. And so, now, why did we need all this anyway? Well, we wanted the slope of the function at x equals 1. So we're just going to plug in at x equals 1, y prime would equal 1/4 minus 3/8. So 2/4 minus 3/8 is negative 1/8. Right? And that's just, if that's the slope of the function, that's also the slope of the tangent to the function, right? Because the tangent line is the line that just raises the function at that one point so that it's parallel to the function at that one place if I zoom in, right? So now I've got a slope, I've got a point, and now it's a piece of cake to get the equation of the line, right? So the point is 1 1/2, slope is negative 1/8, if I plug that stuff into, I already know m. M is negative 1/8. The easiest way to find b would just be to plug in values of x and y. Plug in a solution, a point that's on the line, and solve for b. Yes, ma'am. You can. That's fine. You can use point slope also. I think this is a little easier, but 6 and 1. I mean, if you like that, 6 and 1/2 doesn't matter. Yeah, that's fine. You can use that. So if we plug in y was negative 1/2, right?
Yeah. No, just one.
No, it's positive 1/2.
Oh, positive 1/2. X was 1. So if I plug all that stuff in, I just get 1/2 equals negative 1/8 times 1 plus b. So what's b going to be? Yeah, 1/2. This is just going to be negative 1/8, right? So if I add 1/8 to both sides, 4/8 plus 1/8 is 5/8. So b equals 5/8. So my answer then, I know m, I know b. I just get y equals negative 1/8 x plus 5/8. Okay, which we can see. Yeah. So negative 1 divided by 8.
Tab over.
Tab.
Or not tab. Oh, I guess that.
X plus 5/8. Is that what we said?
Would be correct.
Yeah. Oh,
Yeah, thanks to your test. Can't see it.
whoops. No, I want
Good one.
Okay, well, we got it. Okay, what about this one? Find y prime if y equals 7 cosecant x. Okay, now I got something to say about these. I want you guys, it's my fault, it really is my fault for not having made you do this, but I would like you to know the basic derivatives. You got to know the 6 trig derivatives, and we don't have very many. We have the 6 trig derivatives and the power derivative, a formula for derivative of power. We have derivative of constant, derivative of x. There's not much. And then we have the quotient rule and the product rule. And that's it. And then the chain rule just takes all that stuff and makes it more powerful. The chain rule is not really a formula. It's just a concept. You differentiate from the outside of the onion in. What's that?
We're going to go to channel first.
Yeah, oh yeah, a bunch, yeah. Okay, so I'm going to leave it up to you guys. Have I not passed out the derivative sheets yet?
No.
Okay, stop me with 5 minutes. I want to print them out and give them to you. I'd like you to know those. Okay. So what about this one then? We want to find y double prime if y equals 7 cosecant x.
Oh, yeah.
Okay, so I got to differentiate this, right? So what's y prime going to be then? Okay, now what do I do with the 7?
Leave it.
Leave it's a constant. Leave it out front, right? So I've got y prime equals 7 times whatever I get from the derivative of cosecant. Negative cosecant x, cotangent x. Okay? So then that's negative 7 cosecant x, cotangent x. Okay. So there's y single prime. Now I got to do y double prime, derivative of the derivative. Okay, so what about this now? What's the first piece of good advice that somebody could give the class on this one? What do we do with the negative 7?
Yeah, leave it.
Leave it, right? That's the constant. Leave it out front. So we get a negative 7 times a bunch of stuff. Okay? Well, the derivative of this is what the bunch of stuff is going to amount to. Now, how am I going to differentiate cosecant x times cotangent x?
Break it up into 2. Just
Okay, meaning what's taking derivatives. Differentiation is just a matter of following the rules. So what's the rule that applies here? Well, I mean, what have I got there? Is it a power? Is it a product? Is it a quotient? Is it a trig function? What do we got? It's a
function.
no, it's a product. Because I've got two. See, I've got a multiplication sign there. Right? There you go. So I've got to use the product rule here because I've got two factors that are being multiplied together. So that's just going to be the first.
He's explaining to us everything
Whoops.
and you can map it.
Oh, yeah.
So cosecant x now times the derivative of cotangent x. What's the derivative of cotangent x?
Negative cosecant squared x.
Negative cosecant squared x. Okay, plus the second times the derivative of the first. What's the derivative of cosecant x? Well, we already did it. Negative cosecant x cotangent x. So that's our answer, right? We just need to probably simplify that a little bit.
Probably.
Okay, but the simplifying part isn't that bad. We could factor out with our -7, we could factor out what?
The negatives.
The negatives, sure. Okay, I could take out a -1. Is there anything else I could take out? A cosecant x, yeah.
All the sevens that are in that. Oh, wait,
No,
there is.
you have to leave the same.
I could pull out, what I've really got here, if I want to, I could write this as -7 times negative cosecant cubed x plus, minus cosecant x cotangent squared x. And so the suggestion is take out a negative cosecant x. Why not? If I pull a negative cosecant x out front with my -7, -7 times negative cosecant x is just 7 cosecant x times what? What's left over? If I'm dividing away a negative
Cosecant
cosecant
squared
x
minus
minus
cotangent squared x.
plus, right? Because I'm taking the negative out.
Oh.
Okay. And that's it.
It doesn't make sense.
Okay.
You won't do that last part.
Okay. Okay, so from right here down. Now, all we did was to simplify this. We're just going to try to factor out a greatest common factor. This stuff right here, if I take this first term, that just simplifies cosecant times cosecant squared. Negative cosecant squared is negative cosecant cubed, right? Cotangent times cotangent is cotangent squared, right? And so then I could factor out a negative cosecant x. I could divide that away from each of these two terms, right? Undistributed, which leaves me with positive 7 cosecant x out front. If I divide away a negative cosecant, I take the negative sign away, I take away one of the cosecants, divide away one of the cosecants, 1 power of cosecant, take away all that stuff, making it plus cotangent squared. Okay, well, let's just check it, make sure.
Well, you can't, so.
Oh, well, we'll see at the end, huh? That's too bad. Wish we
Yeah, me too.
Why? Maybe if you
Yeah,
did it.
oh yeah.
could. Yeah,
I wish we had you an example too.
I wish I could do that instead of I did that.
so 7.
Yeah, no, it's like that's 5 different answers on the same one. You can't.
Yeah.
7 cosecant x times, I guess I have to do this, huh? Times, what did we say, cosecant squared plus cotangent squared?
Yep.
Sure. Secants.
Got a good memory.
Cosecant squared
Cosecant,
x.
yeah.
But yeah.
Squared x plus cotangent squared x, like that? There you go. Okay. Body is moving in simple harmonic motion. Here, I'll have to make this bigger. Let's go.
Yeah, let's do this one.
Let's go there. Okay, body's moving, maybe I can. Body is moving in simple harmonic motion with position function s equals f of t, okay, which is just a function of t. So there it is. There's our position function, right? S in meters, t in seconds. Find the body's velocity, speed, and acceleration at time t equals pi thirds. Okay, well, we can do that.
We got this.
Okay, so if that's position, what's velocity?
Derivative.
Derivative, sure. Okay, and we're finding these all at time t equals pi thirds, right? Okay, so v of t is just s prime of t, which is what? Okay, what's the derivative of 8? 0. So then I've got it equals -9 derivative of sine t cosine t. Okay? So while we're at it, let's calculate acceleration. What's acceleration? Yeah, kids, the v prime or s double prime, same thing, right? So we're differentiating velocity. Now, what's that going to give us? Okay, good. I got -9, but the derivative of cosine t is negative sine t. So negative times negative is positive. And there we have it. Okay? So we can plug this stuff in now and find values. So we know that v of pi thirds is just going to equal -9 cosine pi thirds. So where's pi thirds? There. So it's cosine would be 1/2, wouldn't it? The coordinates at pi thirds are going to be 1/2 root 3 over 2, right? So this is going to be -9 times 1/2 equals -9/2. So let's plug that one in.
Doesn't it say velocity speed?
Yeah, okay, so velocity is, what did we say it was, -9/2?
So
what's it doing? I don't know, this thing's a little confused. -9/2, okay? So what's the speed then? Well, it's the absolute value of that. It's always positive, so it'd be 9/2. Okay, and then the acceleration. Well, we got to go back and look. Acceleration. A pi thirds is just 9 times sine of pi thirds. So that's square root of 3 over 2. Okay, so that's going to equal 9 times square root of 3 over 2. So just 9 radical 3 over 2. Or I could put the 9/2 out front, doesn't matter. All right, so let's plug that in. 9 times square root 3 divided by 2. Okay, make sense? And I guess that's it, huh? Next.
Wait, go back 1 second. How'd you know
Sure.
whether or not, why was the velocity negative in the speed?
Why was the velocity negative?
Why was it, yeah, why was it?
Because when we plugged it in, see, -9.
Negative, okay.
Yeah. Oh, okay. And I will put this video up immediately after school, and I'll put the notes up too on this one, so you can, if you want to print them out and have them there or something. Okay. Yes, 246. That'll be up there. Okay. You set? Okay, so an object thrown vertically upward from the surface of a celestial body at a velocity of 30 meters per second reaches a height of s equals 30t minus 0.6 t squared meters in t seconds. So find the object's velocity and acceleration as functions of time. Okay, no big deal. That's what we just did. All right, so we've got if s equals 30 minus 0.6, or 30t minus 0.6 t squared, then v is just s prime. What's that?
30 minus 1.2.
Okay, 2 times 0.6 is 1.2 t. Okay. And then acceleration, while we're at it, is just v prime. What's that? Yeah, derivative of 30 is 0. Derivative of constant is 0. derivative of negative 1.2t is just negative 1.2. Okay. So we can put those in. Oops, I go back. So velocity. So what did we say it was? 30t minus 1.2. No, 30 minus 1.2t.
Yeah.
30 minus 1.2. And negative 1.2. Okay. Okay. It takes the object how many seconds to reach its highest point? Now here's where a little physics comes in. How do we know when this thing is at its highest point? Velocity is 0. Good. We could take this parabola and find the peak, but that's hard. We don't want to do that. It's much easier to just say when the velocity changes from positive to negative, that's when we're going to be at the apex, right? So we could set for this problem right here, we'll just set velocity equal to 0. So 30 minus 1.2t equals 0 when t is 30 divided by 1.2, which is what? Actually, I can go over it. 25, all right, so 25. The object first reaches half its maximum height at how many seconds? Well, what's if the maximum height is 25 meters? Whoops, hang on. No, I think we skipped one. The object takes 25 seconds to reach half its highest point. The object reaches a maximum height of what? Plug it into what? The position function, right? We want to know what's the height, s. So if I plug 25 into that, it's at 30t minus 0.6t squared. Okay, so for this one, we'll make this one red. We want to calculate s of 25 seconds, right? Is 30 times 25 minus 0.6 times 25 squared. We'll just plug that in. So what is that? Find out. That's just $375. So 375 meters. Okay, now did you guys notice that I edited this when I got in and fixed it so it doesn't do the dookie rounding thing? So I did for the test. It's fixed.
That thing.
Remember when you guys wanted you to round it and it was dumb? They wanted you to round it. Okay, the object first reaches half its maximum height when? Well, what's half the maximum height? That, right? Yeah. So 187.5. So we gotta find out when does the object first reach 187.5. So what do we do? Plug it into position. We want to know when is the height 187.5 meters. So we're going to plug that into s. Okay, so then that's going to look like 187.5 equals 30t minus 0.6 t squared. And I gave you your graphing calculators on this one. So this is one that you can solve pretty simply by just either quadratic formula stuff, or why not just graph it and find out. So let's do that. Let's practice that.
Yeah.
Okay, here's one way to do it. This is the MATRAM method. He always likes this one. I'm going to get out of this first. He does. Notice this, Dr. Elias Davis. Okay, so we could graph for one of our equations, we could just graph y equals 30x minus 0.6x squared. For the other one, let's graph y equals 187.5.
Why wouldn't you do minus 180?
Well, because I'm setting this side equal to that side. I want to know.
Move that over there. And
I could. I could. I thought this is the way you did it. Maybe not. Never mind. I don't know whose method this is. Oops.
Isn't that harder than?
Why do you gotta do it the complicated way that nobody does?
Isn't this the way you guys do it?
No, I'm so lost.
Easier, but I don't do it that
Yeah,
way.
like I never
I
would've
do
thought
think
that
this is
way.
easier
That's
because.
easier, but I
It
don't
might be
do it
easier,
that
but I
way.
don't wanna learn something new that.
Okay, how do you do it? You set it
I
equal to
just
0?
put it, yeah.
Yeah.
Okay, we'll do that.
Honestly, not.
We'll do that.
I know, but still, it's gonna screw me up during the test.
Okay, we'll go back. Let's go back and do it the other way. So clear that one out.
Literally no difference.
The reason this one is a little bit easier is because you don't have to make the little guesses. You can just find the intersections easier. So, I mean, it's fewer keystrokes, but that's all right. I'll do it the hard way. That's
I
fine.
want the hard way.
So then we're going to subtract 187.5. Everybody agree? And find the zeros of that function. Okay, so we subtracted this over to this side, and it's equal to 0. So we'll find the zeros of this. So let's graph it. Now let's see. It took 25 seconds to reach the highest point, right? So if we went from like 0 to 50, that'd be fine, wouldn't it? So let's go. I'm going to set the window to go from x min is 0, x max is twice the time it takes to get to the peak, so 50, and then I'll just go zoom 0. Zoom fit and let it pick the y's. Okay, and there it is. So we want the first solution, the one right there, right? So we'll go second calc 0, and then we'll just track that one. So my left boundary, I'm going to say 5, rather than have to trace. So there's that one. Right one, 12, and you could just trace if you want to. This way. There's my guess in between somewhere. And so the answer is 7.32 to 2 decimal places. Okay, the object is aloft for how many seconds? The answer is 50. Yeah, you actually know that. That's now maybe you didn't see that, and I'll show you how you can find how we could find this thing without knowing this little trick. But what Tanner's exploiting is the fact that this object has symmetry on the way up and the way down, right? Gravity acts on it the same way. That's pretty tricky. It's slowing down the object's upward motion just as fast as it's speeding up its downward motion, right? So, yep. So that's a classic example in physics of a reversible problem. If we filmed it with a camera, if we
Physics kids have an upper hand on me.
a little bit on this one, but they should because physics is the greatest thing ever, and you should be taking it.
I'll take it in college.
There you go.
Calculus applied.
There you go. All right.
He's an engineer.
If you filmed a ball going up in the air and coming back down, you reverse the camera, you couldn't tell the difference. It's absolutely identical in the absence of errors.
That's actually really cool.
So here's the other way to do that one, though. This last one. The object is aloft for how many seconds? Well, when is it on the ground? It's on the ground when it's first fired and when it comes down, right?
Yeah.
So when it's on the ground, what's the height?
0.
0, right? So we're just finding the zeros of the position function. So we would just set 0 equal to 30t minus 0.6t squared. That's a pretty easy one to solve. We could factor out a t. I mean, we could just graph it, but it's much easier to just factor out a t, and then we're left with 30 minus 0.6t. So my zeros are either t equals 0 or t equals 30 divided by 0.6. If I set this one equal to 0 and solve. So 30 divided by 0.6 is 50. So there's your 50. So that's when it hits the ground for the second time, which is after it's been in the air. Okay, so I'm not even going to bother putting those in. It takes 2 minutes. Find the horizontal tangents of the curve. Okay, all we want are the values of x where we have horizontal tangents. Now, what's our strategy here? I'm not sure if we'll even do this one. Zeros of the derivative. Exactly. So we know that the derivative stands for the slope of the curve. The slope is going to be 0 when the tangents are horizontal, right? So we could just do this. We could say, well, y prime is what? We'll just differentiate term by term.
3x squared minus 22, there it's 12.5.
Okay, and we want to just set that derivative equal to 0 on our calculators and solve.
Okay, next.
Okay, right? No big deal.
We got it.
Those are going to be probably decimals, integers, or fractions. You want them as fractions, that's okay. Your calculators will even give them to you as fractions. Can we skip that one for now?
Yep.
Okay, I think there's... Okay, here's one I want to do because this is chain rule deal. We haven't done much chain rule stuff yet. So let's find the derivative of y. Okay, now at the outermost level, what kind of an animal are we talking about here? It's multiplication. Yeah. Right? I've got a product of x cubed times the quantity 2x minus 1 to the 7th. So we got to use the product rule, right? Okay, so y prime equals the first times the derivative of the second. Now the derivative of the second is going to be a little complicated. What's the derivative of 7 of hand to the 7th?
7 hand to the 6.
7 hand to the 6th. So there's the first layer of the chain times 7 hand to the 6th, and hand is 2x minus 1. So then if I peel away that outside layer, what's the derivative of what's inside? The derivative of 2x minus 1 is 2. So I got 2 links in my chain rule. Okay? Plus the second, which was the quantity 2x minus 1 to the 7th times the derivative of the first. What's the derivative of x cubed? 3x squared. Okay, so there's our answer. Now we just have to simplify things a bit. Now it might be useful to clean up the first term and the second term separately. So it looks like here I could pull the 7 times 2 out front as a 14. So I get 14x cubed times the quantity 2x minus 1 to the 6th plus 3x squared times the quantity 2x minus 1 to the 7th. Now, when I factor out greatest common factors here, notice that I've got 2 like bases. I've got x's, and 2x minus 1s and 2x minus 1s. I'll take out the greatest common power of each, which is the smaller of the 2, right? So what's the biggest power of x that I can yank away from both of those 2 terms? X squared. So then we get, and I can't take out any numbers, can I? 14 and 3 have no common factors. So I can take out an x squared. What's the greatest common factor of the base 2x minus 1? To the 6th. Leaving me with what?
14.
What do I get from this one? 14x. Right? Because I took the entire 2x minus 1 to the 6th, I divided it out front. Plus, what about this term, this guy over here? I got 3 stuck there. I divided away the entire x squared, but I only divided away 6 powers of 2x minus 1. Yeah. Say it again. On this line right here,
Above.
Blue 2.
the blue 2 by the chain rule, okay? Because when we differentiate 2x minus 1 to the 7th, I got to differentiate from the outside in. So first I've got 7 times the quantity to the 6th, times, I got to peel away that outside layer, times the derivative of what's inside. That's where I get the 2. Okay? Okay, Danielle, question? Okay. So the way I'm coding this, the reds are going to be the first derivatives, blues will be the second derivatives, and then if we need to, we'll keep going. Okay? So then down here we just get, except down here I kind of screwed it up. 3 times the quantity 2x minus 1 to the 1. So I could combine all this stuff into a single factor and we're done. So we just get y prime equals x squared times 2x minus 1 to the 6th times 14x plus 6x is 20x minus 3. That's it.
Simple.
Okay?
That's the final answer?
That's as much as we can do.
Okay.
Oh, okay. Okay. All right. This guy, I guess. Huh? Is that the next one? Yeah. Okay. Find. Okay, this is a good one. This is a good. I like this a lot because here's a chain rule problem where it's a good idea to rewrite it. Now it's hard to see here, but what's the outside layer of this thing? Is it a trig function? Is it a power? What is it? It's actually a power. Okay, here's why I think it's a very good idea to rewrite these. This one, when you have a shortcut trig power like this, if you rewrite it as the quantity sine of 2 pi t minus 1 squared, it becomes obvious then that the outer layer is a power. But you don't see that so much when that power is buried inside there like that. Okay, so I strongly recommend you rewrite those. When we differentiate this then, at the outermost level it's a power, so I've got, what's the derivative of arm squared? 2 arm to the 1, right? So this is going to look like 2 arm to the 1, and arm is the sine of 2 pi t minus 1. So if we peel away that outer layer, right, so let's just do that up here. So this guy is gone now, right? What's the next layer? I guess I can take that away too. Once I take away the power, now it's a trig. I've got the sine of hand. Well, what's the derivative of sine hand? Cosine hand. Okay. So I'm going to multiply that by cosine of hand. 2 pi t minus 1. And then if I take away the trig part now, I've differentiated sine, what's left inside? 2 pi t minus 1. What's the derivative of that with respect to t? 2 pi. Good. Okay. There it is. And just so we don't get confused, let me build this back. That was a
This should
sine squared, right? All right, so then we could clean this up a little bit. There's not much to do. What could we do here? Yeah, I could take the 2 pi as a constant out front with the 2. So I get 4 pi times, and then I've just got sine of this times cosine of that. Okay, there you go. Now, this isn't what they want, but does anybody see this? Here's what I would do with this one. I would call this 2 pi times sine of 2 times 2 pi t minus 1. Using the double angle. 2 sine of hand cosine of hand is the same as sine of 2 hand. But they don't want that. I'm just showing off. So that's what you want.
Oh my God.
Can you explain? You're showing off again.
This is just, this would be this is a pretty cool way to do it.
Okay.
Can you put it in like that?
I understand that.
I don't know, maybe.
I'm not gonna try it. I'm not gonna take the whole freaking test.
But what did you say? How did you say you got that? You said it was.
Because we know the double angle formula says 2 sine theta cosine theta is the same thing as sine of 2 theta.
I'm gonna have,
Okay.
Okay.
I never know when to stop.
Okay, how about this? We've done a bunch of this.
Yeah, next.
Okay, next, yeah. That's a good one. Should we do that one? We have time?
3 minutes.
Okay, we can do it. So f prime of x. Now, outermost level, what is that? Power. Derivative
Hey,
of...
we need our derivative papers.
Yeah. You got the stuff.
Oh, yeah, we do. Okay, hang on, I can do it. I can do it. This is right here.
You can't do it and show it.
Oh, yeah, you don't think so?
No.
I'll stay here
man,
for
I
3 minutes.
dare you to try.
I
double
dread
dog
the
dare
volunteer.
you, just like you always do.
Where's the derivatives? Right there, basic derivatives. That's it. That's what I'm looking for. That's what I'm looking for. Okay. Print. How many copies? Like 18. Okay. All right. So back to business. That's printing. Somebody who wants to be, go get that for me.
Then that person won't learn.
Do I look like a mouse? Lab rat?
Okay. At the end, we'll walk by down there and get them on the way out. Okay. So. Oh.
Finish it now.
Okay. So. Okay. So we got hand squared, right? So the derivative of hand squared
Is 2 hand.
equals 2 hand to the 1. Well, hand is sine x over 1 plus cosine x. Now the derivative of what's inside, how are we going to do that? Quotient. Yeah. So then we've got inside there, we're going to have something big and ugly. We're going to have, yes.
Oh, and she is.
Bottom times derivative of the top. What's derivative of sine? Cosine. Minus top times derivative of the bottom. What's the derivative of 1 plus cosine x?
Negative sine x.
Negative sine x. Okay. All divided by the bottom squared. Okay. So we got some stuff going on here quickly. We got 2 sine x times 1 cosine x plus cosine squared x plus sine squared x. Sine squared x plus cosine squared x is 1. Cosine squared x plus 1. Cosine x plus 1. We ran out of time.
Yeah. Wait, are you going to be done tomorrow?
No, I'll be here tomorrow.
Okay,
We can
review
finish
that
that
really
tomorrow.
fast? Yeah.
Oh, okay, we'll finish that one tomorrow. Okay, swing back. Let's go by the room and I'll get you your derivative sheets.
Crap, I have leadership.
Actually,
Where are you putting this up right now?
I am not a leader.
Follow it.
I do not wish to partake.
Hello. How fresh? That would grab my name for. Don't change it. It's right forever. Never. Lame. Never. That's a clever response. Yeah. I thought so.
no.
Yeah, because I was trying to be like a bird, Courtney. You're horrible. You're a horrible person, Courtney. Thank you. That was so horrible.
You get over there and you give her a formal apology.
I already did.
A formal apology.
I'm sorry. Thinking you would.
There you go.
Did you get one of these?
No.
One that goes all the way down to my knees.
I was working on your
All right. Battle of the boards.